Papi, are we good to go? Professor Shanti?
Yes.
People are joining, so just give me 2 more minutes.
Sure. So when
1
Gopal
minute.
Kumar is introducing, please put him on spotlight.
Okay.
Okay, all the best.
Thanks.
Shall we start, Nishani?
No, 2 minutes. Papi, I will give you a cue.
Yeah, 2 minutes because people are.
Yeah, we've received 170 registrations, so we'll give them a minute or so. Highest registration so far.
There is always a gap between the registration and the attendance.
That is true. That is true.
Having registered for many things myself, I can say that confidently.
That's true.
So how, do you normally let people ask questions in between or?
Normally, what?
Only at the end, last 10 to 12 minutes.
Okay.
And we asked to type the questions in the chat box, then it will be easy for you to.
Okay.
Yep.
I think we can start.
We can start.
Yeah.
So this program will be live stream in YouTube. So it will take 2 to 3 seconds to, the pause will be there. So please, like, as soon as it will start, then after 2-3 seconds, you just start talking. Yeah. So Gopal Kumar, sir?
Yeah. So hello, good evening, good morning, good afternoon. Hello to everyone. And I am Dr. V.T. Gopal Kumar. I am working as a professor at Adi Shankara Institute of Engineering and Technology, Kaladi. It is managed by Sringeri Math. And Guru Talk is one of the prestigious activities of IIT Madras Alumni Association. I welcome everyone to this Guru Talk. Today's speaker is Professor Shanti Bhattacharya of IIT Madras. Before I introduce Professor Shanti Bhattacharya, the topic in brief. So the title of the topic is Shrinking Optics and Infinite Possibilities. And the primary purpose of light was illumination has gone. And today light is shaped into beams with interesting and non-intuitive behavior for a variety of applications. This complex light, as it known, can be created using expensive tunable spatial light modulators. But Dr. Shanti's group, however, they design and fabricate diffractive and meta-optical element as a compact means by which to manipulate the light. In this talk, she will be looking at how these optical elements with the micro and nanometersized features carry out tasks not always possible with the conventional optics. So it is my privilege to introduce Professor Shanti Bhattacharya. I am one of her students as well. She obtained her PhD in physics from Indian Institute of Technology, IIT Madras in 1997. She was awarded the prestigious Alexander von Humboldt Award in 1998 and worked at the Technical University of Danab, Germany for several years. Then she joined Analog Devices, Cambridge, USA as a design engineer. At present, she is a professor at Department of Electrical Engineering, IIT Madras. And she is served as a board of OSA, Optical Society of America. Now it is known as Optica, and currently an associate editor of Optical Engineering. Her current research interests are meta and diffractive optics, optical MEMS, and studies related to imaging techniques. There are 136 international publications credit, both journal as well as conference papers. Also, she is author of one of the textbook along with the students in diffractive optics, and she is an active in sponsored researchers as well. As of now, she has received an amount of rupees 149.1 crores of rupees in the sponsored research categories. While she loved her work in the light, she also loves her breaks as well. She is an enthusiastic hiker and enjoys several outdoor activities. So on behalf of IIT Madras Alumni Association, I welcome all and welcome our speaker, Shanti Bhattacharya, for this wonderful event. Madam, over to you, Madam. Shanti, Madam.
Thanks a lot, Gopa, and thanks to everyone at the IITMAA for this invitation and organizing this. It's always a pleasure to talk about my work. So without further ado, let me start. I'm going to be introducing one aspect of the work I do, which is on micro nano optics. And I've called the talk shrinking optics because infinite possibilities, because there are so many things that one can do with this optics. Oops, sorry. So this image or these set of images are just a very small fraction of the things optics are used for today. So you have these huge bridges, and the health of these bridges can be monitored using optics. This is a sophisticated imaging of retina. This is of the cochlea, part of the ear. And here's we've been, not us, but people have studied different modes of a musical instrument. And there are maybe some more familiar objects here. Unfortunately, the pulse oximeter familiar to all of us now because of COVID. A smartphone, a microscope. Very disparate, some small, some large, some allowing us to zoom in and look at very small structures, some very big structures like the bridge. The connection for me, at least, is that they all have a very strong optical component in them. So it's really obvious that today, light is not used only for illumination, but it's used a lot to give us data and give us information, and that can be done in so many different ways. So in today's talk, what I want to be able to show you is that because we are using light for things other than illumination, it's not enough to switch on a light source. It's not enough to switch on a bulb and just take the light the way it is, but we need to modify that light in some way to make it more useful for us. And that's really what I'm going to be talking about today, to convince you why that is important, and then to tell you how it can be done, and to show you specifically some techniques that we use in our lab. So why do we need to shape light? So if we look at one of the common sources that we use, it's a laser. For many of the applications, we use a laser. And the output of a laser is as shown over here. If I have a laser coming out of a beam coming out of a laser, and I look at a cross section of the beam, you'll see that the intensity actually is very bright in the center, and it reduces as it goes off to the side. So immediately there comes a need for shaping or changing it, because say I'm using this laser for some material processing, I need to heat up something, some workpiece, and I don't want that the central part of the workpiece is hotter than the rest. I want to provide a uniform amount of heating. So I need to convert this beam into something with a uniform intensity. So I need some kind of element that will do this conversion. Alternately, maybe I want to cut out a circle like you do for cataract operations. So I don't need to provide heat all over a circular area, but I just need to provide heat in a ring. So instead of wasting that energy in the middle, if I could somehow convert this Gaussian beam, that's what this intensity distribution is called, into a ring, then I have used the power much more efficiently. And in the cases of something like the eye, it's also probably much safer. So I need some kind of transformation optics that transforms the output that I get from a laser into a shape or form that is useful for the application of interest. Another very common example today, and maybe not so easy to understand or familiar to the layperson, is that of a Bessel beam. So a Gaussian beam is what we get out of a laser. This is how its intensity profile looks, very bright in the center, falling off towards the edges. But I can also use something called a Bessel beam, which has a very sharp inner core with this ring-like structure around it. So if there's some way to convert the Gaussian to the Bessel, that would be excellent. Why am I interested in the Bessel beam? So if you take a Gaussian beam of a certain diameter and a Bessel beam whose central radius has the same diameter, as these beams propagate, so these graphs are showing you the beam traveling, and you can see that the Gaussian beam spreads out a lot as it travels, whereas the central part of the Bessel beam stays for a very long time, almost the same size. Why is this of interest? I'll get to that, but let me just convince you of that a little further. Here's a little schematic showing you a Bessel beam in purple, the transverse view of a Bessel beam in purple and that of a Gaussian beam. Both start off at a distance with the same width, but as the beam travels, you can see that the Gaussian beam starts spreading out, whereas the Bessel beam almost has the same width. And after a distance of 5 centimeters in this particular case, you can see the Bessel beam has spread out so much, but the Gaussian beam has spread out so much, but the Bessel beam has stayed quite narrow. Where is this useful? Well, so we call this diffraction free, but really what it means is it doesn't spread that much. And it has one more really interesting property. If you take the Bessel beam, and in this case, the beam has been transformed and you have the Bessel beam. And now let's say you introduce a small obstacle or block. So I'm not sure if it's clear, but over here you block the beam. But as the beam travels beyond the block, and the subsequent images here, it shows 2 millimeters after the block, 4 millimeters, 6 millimeters, and you can see that the beam has reconstituted itself. It has healed in spite of being disturbed at this early point over here. This is very useful because let's say you're using this beam to image. So you're sending this beam through, say, tissue. Tissue is a highly scattering medium. The light is scattering. And you can see with the Gaussian beam, it will easily scatter. Whereas in the Bessel beam, this is a schematic. There is, of course, scatter, but there will be less scatter. It will be able to travel further through. And so you might be able to image deeper into the tissue, for example. I've put this video here. This is from a company. Let me just run it and show you that this is another application of this kind of complex light or specially shaped beams. You have a set of blood cells here, and they've been trapped by 9 beams. So I hope the video is playing. Hope you can see that. So this is from this company, and they've shown that these 9 blood cells have been trapped and they're able to move them around. So this allows you to hold blood cells or certain cells or molecules in a particular environment. It allows you to apply certain forces on them and to see how they deform. And that allows clinicians to understand if there is a particular disease or if there is a certain problem. And so it's very good for diagnostics. Now, all of this is possible with special types of beams. In fact, this kind of work earned Arthur Ashkin the Nobel Prize in 2018. These kind of beams, the work on these kind of beams. So I hope with that, I've convinced you of the importance of shaping light. And it must be pretty obvious that you can't take light directly out of a light source and have it do all these wonderful things. So we need to manipulate the light. And in our group, we actually call ourselves the master manipulators because that's what we do. We spend all our time figuring out ways to efficiently manipulate light. So what our research goal really is to take an incident beam, typically a Gaussian, and we want to design and fabricate some element that will transform this Gaussian beam into some specific shaped light, complex light. In other words, light with a specific desired behavior. So our research problem is, how do I get this element? How do I get this element that will give me the desired output? So I'm going to answer that question by using this figure. This is an image of a fire, and you can see the light that is coming through this image to you, but in the region around the fire, it's quite blurred. Whereas if you go quite far away from the fire, you'll see that you can see the image very clearly here, whereas you can't see it very clearly in this region. And the reason for this is because of the heat, there is a change in the refractive index of the air above, and it's in fact fluctuating as the temperature is varying. So you have this varying refractive index. And for optics, this is very important because it means that the phase that the light is seeing is changing. The refractive index and the distance traveled by the light together affect phase. And here, the phase is continuously changing because of the temperature changing. And therefore, that is why we are seeing this as a blur. We are going to use this concept of phase to help us manipulate light. In the previous image, it caused a bad image. We couldn't see clearly. But if I cleverly manipulate phase, I can use it to cause the change I want in the incident beam. So in this schematic, I have a single uniform thickness glass slab. It has a constant refractive index. It's not varying as in the previous image. And I have a plane wave that's traveling. Now it travels up to the glass slab. And in this glass slab, it's going to slow down. But because it's uniform, everywhere along the beam, it changes in the same way, it slows down in the same way. And after that, it will continue as normal. So I have affected the phase, but I haven't got a very useful change. I give you an example which is maybe more familiar to you. Let's take now a glass slab that's shaped like this. And this may be a shape familiar to you. This is nothing but a convex lens. So now, when the light travels through this, different regions of this wave, the region here sees a certain thickness of glass, whereas the regions towards the edge see a different thickness of glass. They are slowed down for a different time at different places across the lens. And this causes the plane wave to change its shape. And in fact, we're using the radius of curvature, we're using the material property, the refractive index, and together we're changing the shape. And of course, we use such pieces of glass or such shaped elements for imaging a system. So we've already used to this concept of using phase to change light in such a way that it gives us useful information. Here, it's helping us to create an image of something. What we do in our lab is not to use refractive elements like what I've shown you here. These are lenses, but we use diffractive elements and meta-optical elements. The very big difference of these elements from refractive elements is if you look at the feature sizes. Here is a diffractive element, and it has very small feature sizes. The spacing over here would be in the order of wavelength. This is an example of a meta-optical element. The diameters of these little cylinders here would be in the order of sub-wavelength. So we are talking about feature sizes which are in microns or which are in hundreds of nanometers. And this is where the title of my talk comes from. We're shrinking these sizes, but with these shrinking sizes, you can manipulate light in ways you cannot with refractive optics. Okay, so you're really talking very small feature sizes here. What does this give us, these very small feature sizes? Well, as I said, and as I will show you, you can do tasks which you cannot do with conventional refractive optics. You can make systems really very compact. Meta-optics, the other term for it is flat optics, because you don't need bulky optics with a large curvature. You get that phase change from this flat optics itself. You could combine different functions and put them onto this thin phase variation. And you can even beat the diffraction limit very cleverly. And that was, in fact, another Nobel Prize winning discovery. It was granted in 2014. So just to give you a quick example, if I took a plano-convex lens and I remove all the regions of this lens which contribute a phase change, which is equivalent to lambda, that is a phase change of 2 pi. If I removed those phase changes, what I would be left with is this. But this structure is quite hard to fabricate because unlike this refractive structure, which has one large smooth variation, quite easy to fabricate, this structure now has very small regions and it would be very hard to fabricate these. So we create an approximation to this, which we call a binary element, because it has only 2 levels. It doesn't have these analog continuously varying levels. We just have 2 levels, and we can create an approximation to this, which luckily for us is able to carry out the task of this lens, albeit with some disadvantages, which we'll come across later in the talk. But there are enough promising advantages that you're able to create binary diffractive elements in this way. And this is a very simple example. You might have seen Fresnel lenses used in lighthouses. They may still be refractive if their feature sizes are very large, but that same idea, if I shrink down the feature sizes, then I'm into the regime of diffractive optics. So this is a very simple way of creating diffractive optics. You could think of diffraction as having, so I have that same lens over here. I have a single beam. This red rectangle here is showing a single beam incident on this diffractive optical element. And because of all these different regions here, it's as if you have different beams traveling and they all interfere with each other. And because I have all these different beams interfering with each other, I'm able to make them do certain things. If they in phase, something happens. If they interfere out of phase, something else happens. In some places, they're in phase. In some places, they're out of phase. In some places, they're somewhere in between, and therefore I can modulate that light to have a very specific behavior. I like to say that this combination results in desired light behavior, and you can think of interference as a couple of musical instruments together that can sound really good, but in diffraction you have the whole orchestra. You have infinite number of beams that you're pulling together, and you really can produce wonderful light patterns, very useful for a large range of applications. So I hope I've been able to convey why we want diffractive. I haven't gone too much into meta, but I'll go into meta-optics later. But really what we're doing both with diffractive or meta-optics is creating fine features. And what are the variables I have, or what's the toolkit I have to create those features? Well, I can change the lateral dimension of this feature. I could change the height of this feature. I could change the shape of this feature. I could change the material, the refractive index. So in the schematic, I have some kind of cuboidal fine structures, very finely spaced, but I could even have these kind of pyramidal structures. This is actually a figure of a grating fabricated in our lab. And you can see this is of the order of hundreds of nanometers. Using all these design parameters, I can create structures or elements which will modulate the light in a way that I want. Okay, so how do I calculate that phase? I've told you what I need to do. I need to create this fine variation of these fine features, but how do I know what those features should be? What's the phase that I need that will convert the Gaussian beam or the incident beam into the beam of my choice? So there are different techniques to do this. I could start with a convex lens, as I showed, a known refractive element, and go from there to a diffractive element. That's one way. So I'm taking an existing refractive element and doing this, and I might do it because it makes it more compact. I could say, well, I know I want to generate a Bessel beam. I want to generate a beam with a certain behavior, and I have the equation of that beam. This is just an example. I have the equation of that beam. So from the equation of that beam, I will generate an element. Maybe it looks something like this. And let me, maybe I didn't make that clear. This, when I'm showing you these regions of black and white and gray, these are all phase elements. So that means the phase is varying. White could be 2 pi, white could be pi, black could be 0, and all the grayscale are all the regions of phase in between. That means these elements are completely 100% transparent. All the light goes through, but different regions acquire different phase. And these different beams that have acquired different phase, they are the ones that combine to give the pattern of our choice. Okay, so I can, as I said, I could be using a refractive element and converting it to diffractive, or I could be taking a known equation and from that generating the element. Or I could say, this is the beam I have from my laser. This is the beam I want for this application. Now I can run an algorithm which says, from this beam to this output beam, what should the phase element be? So I use an iterative algorithm that goes from my input to the desired output, and it calculates what should the phase look like in between. And I might get something that looks very random, but such a random phase might have some image information stored in it. And when I illuminate it, it will create the beam or image that I want. So there are multiple ways of getting the phase that I need that will convert the output of a laser into the desired beam. Okay. So if you think diffractive optics is new, hasn't been around for much, I'm sorry to tell you, we've already been invaded. It's a large market, and I took this from a recent report which says the current global market is so many $100 million and is supposed to grow also quite a lot. Where it's used in bulk is in gratings, used a lot in spectroscopy, in scanners, in beam shaping for the applications I've told you about, splitting, laser material processing, and a lot in biomedical equipment. So there's a lot of diffractive optics already in many of the systems that we use. Okay, so we've walked through why we need to shape light, how you can do it with phase, how you can calculate the phase. And now I want to go to, well, how can I do that fabrication? How do I fabricate it? I know this is the phase variation I want. And that phase variation is going to be in terms of a height variation. So there's going to be an optical element and the height is going to vary. And because of that, light is going to travel in some regions of thicker glass, some regions of less glass. And I now need to be able to fabricate this. I need to actually make it. Fabricating refractive optics, it's been around for centuries now. You can take a glass slab. Maybe the glass is softened a little bit and crudely made into the rough shape. And then it is some kind of milling process is used to get it into the shape of the convex lens or whatever optics you want. So you're doing some kind of mechanical machining. But for nano optics, because of these very fine features, you're typically not doing mechanical machining, but some kind of lithography technique. These techniques are commonly used in the semiconductor industry. So there are many of the same techniques, those ideas are borrowed here. We may use electron beam lithography. You can write very small features, less than 100 nanometer size. Photolithography, you can write features about a micron in size. focused ion beam lithography, where it's actually an ion beam which is milling, it's physically removing material, again, very small feature sizes, and something called direct laser writing. I don't want to go into the details of these lithography techniques, but we have access to some of them at IIT, and some of the work I've done using the direct laser writing is with collaborators in other institutes. But the point I want to say is that you need these kinds of sophisticated tools in order to fabricate these optical elements with these very fine features. And you can really do very interesting and very fascinating things with them. Just to give you an idea, just of one, I've got a process flow for photolithography. So maybe you would make a mask. This might be related to a diffractive optical element you want to create. So you have a glass sample and you have a material, a resist, which is sensitive to light. So you will expose this material through the mask, and the regions which actually see the light, they get affected by the light. And depending on the type of resist, that material may either be removed in a chemical washing or developing process, or that material may stay firm. Either way, I have transferred the pattern that this mask had into this material. And now maybe I will use this directly. This is my optical element, or I might use this and further do some processing and transfer this into the substrate below. The important or the simple idea to take away from lithography is that I'm transferring a pattern from a file or a mask into a material, and maybe do a couple of processing steps, but finally I have an element which has that pattern in it. And this is how I transfer that phase that I want, that variation in height, into a material, and that becomes my optical element. Now, just to keep in really on topic here, shrinking optics, I want to show some work we did where we put optics on the tip of a fiber. So communication fibers are 125 microns wide, and the core of the fiber, where the bulk of the light travels, can be anything between 8 to 10 microns wide. And it's very convenient, or it would be very convenient, to put your optics directly on the fiber, because fibers, they're made of glass, so they're quite inert. They can survive quite harsh environments. You can send a fiber into regions which are very small, hard to access by people or other bigger instruments. So you can send your light into regions, and instead of having optics after the fiber, which collects and shapes this light, you could have the optics directly on the fiber so that you send the light out with the desired behavior. So this is an image. This is a surface of a fiber. You can see this structure, the diameter is 10 microns, and within that 10 microns, you have these fine features. In fact, these features will create a bezel beam. So the light will travel down the length of the fiber. You can't see that here. The fiber is behind this image, but it would emerge. Normally, it would just emerge out of the fiber as a Gaussian beam. But now it emerges through this optical element here, and it becomes a bezel beam because of the pattern that is formed on the core over here. So I don't have to align a separate optical element after the fiber. Many people, actually I shouldn't say many, a few people have been working on this, and you can see they've actually here made a refractive element using ion beam milling, and there are other pictures of diffractive elements made on fiber tip. You can use direct laser writing. This is ability to move a laser around in a material, but only where the point of focus is do you affect the resist, and you can make really remarkable 3D structures. Again, this is a fiber surface. And on this this was just done for demonstration. But the work that we actually did was, on the surface of the fiber, we put a little prism so that the light that came out of the core, this dark black region is indicating the core. So light that comes out of the core would hit the side of the prism, totally internally reflect. And then we had put a grating here, and it would hit this grating. Now, if the light had a certain polarization, it would travel on straight. But if it had a different polarization, it would be deflected in this direction. So you can imagine that this fiber has collected light, and the polarization has some information in it. Each polarization has different information in it. And I can use this whole structure, which is directly written on the edge of the fiber, to separate out these polarizations and to get the information from each polarization immediately after the fiber. These are schematics that are shown here of how this would work, and the actual fabricated structures are shown here. This is false colored just to make them clearer. So this is all done with a direct laser writing system with collaboration from Karlsruhe Institute of Technology. And this is the prism. You can't see the core anymore because the prism is sitting on the core. And this structure just is there to hold up this sub-wavelength grating. So the light would be coming from the core, hitting the side of the prism and hitting this grating at a particular angle and separating out into the two polarizations. So that's the full SEM picture, microscope picture showing that structure. Okay, so I've talked about some micro optics, and I've talked about how you can fabricate it. But I want to now go a little bit into meta-optics because I've really been focusing only on diffractive optics. So since I can do so much with diffractive optics, why are we even interested in looking at some other way? What I didn't mention all this time is the moment I have a binary diffractive element. So this is a grating. It has just two levels. When I illuminate it, I always will get orders. I can never get a single beam of light. And in fact, I will get many orders. I could design my grating very carefully to get rid of the 0th order, but I will always have some higher orders. I can't avoid this. What we do is we design this structure so that one order has the information or does the job we want, and I block the other order. So it's inefficient. I have all these orders, but I'm going to block them. I'm going to hide them and use one order. This is not efficient. And sometimes those other orders, they scatter and they may cause stray light in my system. So they may reduce even the quality of the image or the work I'm trying to do. So meta-optics changes phase in a different way. I know I need to change phase in an element so that I change the incident beam to an output beam. I've shown you how to change phase with diffractive optics, but meta-optics changes phase in a different way. And the people who first thought of it present this idea by saying, think of Huygens theorem. We are all familiar with this, would have learned it in school, definitely in college, if you did engineering. We know that a wave travels, and it travels by saying every point on the wave acts as a secondary point or a secondary source from which the next wave goes. And using this idea, we said, what if we can engineer these secondary sources so that they don't just give me the same phase difference everywhere, but I engineer each of these point sources so they give me a different phase. And we're able to do that using sub-wavelength structures. And say, for example, this would have been a binary version of a prism This is a diffractive version of a prism, sorry, not binary, a diffractive version of a prism. Now, if I was doing this in meta-optics, this gradual change in height, which is a gradual change in phase, I could achieve it by just putting small structures of different diameter. They're all the same height, but the lateral dimension is changing. They're all smaller than the wavelength of light. So they're all sub-wavelength. But because they're sub-wavelength, the way light sees it is very different than the way light sees a structure which is much larger than the wavelength. And in fact, what happens here is these sub-wavelength structures act like point sources, causing different phase values. This is why meta-optics is called flat optics, because they can be very flat. All the structures can have the same height, but the different lateral dimension is what is causing the different phase values. And now I can create a structure, a prism, just by changing these lateral sizes. So here a student has created what we call a fork grating, and this generates a beam like this. This is used for the kind of trapping that I showed you in that video at the beginning of the talk. And here he used these cylinders. He used cylinders like this, but he used only two types of cylinders, two sizes. So it's not a very good representation of the analog phase. It's just two. It's like a binary element. And you can see that the ring is very poor efficient. There's very less light going into the useful order. Here we've used cylinders with four sizes, and the ring is becoming more efficient. More light is going to that order. And here we have cylinders with 8 different sizes, and you can see it becomes very efficient. Most of the energy goes into one order. And this is a big advantage of meta surfaces. We can make them highly efficient with just two binary heights, two heights, and yet we can have 8 or even more levels. Okay, so I just need to check how much time I have. Okay, so this is a zoomed in version of this structure here, and I'm just showing you two different phase structures. So this is a cylinder of 98 nanometers. This is of 172 nanometers, and these would contribute different phases to the incident beam. And in the 8 level, I have 2 more sized structures, different sizes, but 2 more such structures. Sorry, I have 6 more size structures. So I have cylinders, 8 different size cylinders, which together give me these 8 phase levels and allow me to very efficiently convert the incident light into the desired output light. So I'm actually almost at the end of my talk. I summarize what we do in our group. This is a very busy slide, what I tell my students not to do, but let me just tell you, it basically means we do a lot of different types of designing. If you give us your requirement, we can convert that using different software into a meta-optical design, into a diffractive optical design. And in fact, we have developed some software which it's freely available from our website. So if you already have a design, you could use this software to convert it to the language that is required by lithographic machines, so that they can take that pattern and write it, or use it like if you want it for an e-beam lithography or so on. So we can create all kinds of designs, and we can also create designs for meta-optical elements as well as for diffractive optical elements. We also, of course, do fabrication. So this is a structure fabricated with a focused ion beam milling system. This was in the fiber itself. This is in a glass, and we have this triangular shaped grating. And here, this is a sub-wavelength grating. So these gratings, if light of different polarization falls on it, it will see it differently and behave. One polarization will travel in a particular direction, the other polarization in another. So it separates out polarization. And here we have an element that will transform an incident beam into a beam that's called an airy beam. And it has a property that it travels. It's like it has some properties of the bezel. It will self-heal. If it sees a disturbance on its path, it will heal after that. So it can travel further in a scattering medium. Plus, it has some other interesting properties. It's very useful for imaging. So to summarize, we take a design, we can create complex light, whatever you can imagine light. And of course, we can fabricate, and we're looking, or we work with people who have different applications. This is some of my group members working on areas related to what I talked about today. And yes, of course, none of this would have been possible without my students, my staff, and funding agency. A lot of these are all Indian funding agencies. We do our fabrication in-house in our fabrication facility here in the Department of Electrical Engineering. And of course, I have also had a lot of funding from the Humboldt Foundation in Germany. Again, I thank my collaborators, and I've listed out the collaborators on work that I've done, that I've shown you today. So with that, I thank you for attention. Thank you very much for joining me on a Friday. I'm sure all of you had other things to do, and I'm very happy to take questions.
Professor, some questions are already typed in the chat box, so please go.
Okay, let me just open that. So there's a question, why does the bezel beam behave the way it does, assuming both beams propagate through the same medium? So this bezel beam has this property of self-healing. So that means if at one plane it encounters some scatterers, the beam has the ability, let me see if I can go back to that slide. Trying to get out of the slideshow mode. Okay, I'm not able to change my slides for some reason. Yeah, that's what I wanted. Okay, so if you see the cross section of the bezel beam over here, right? It has these rings. So this central core gets blocked and disturbed, or some part of these rings get blocked and disturbed. But what is happening is energy is coming from the rest of the ring. They are coming back into the beam after the disturbance. So even though it got blocked by a scatterer here, the rings contribute later on in the beam. And so that means the beam self-heals and it can travel a little further. Whereas in the Gaussian beam, if it got blocked, it doesn't self-heal. And so it will not travel further in that whole region because it got disturbed. So the bezel beam, the trick is that there is energy in all these rings. You're blocking some part of the beam, and then the rest of the rings are helping as the beam propagates to bring back energy and reconstitute the beam. So it allows, of course, it has limits. It's not that it can go to infinity, but it has some better propagation than Gaussian. So I hope that answered your question. Is there any, there's another question, is there any advantage with diffractive or meta-optical elements to reduce loss of power in the beam compared to refractive lenses? Actually, I would say refractive lenses have less loss, right? Because you can take a single refractive lens, you could put a thin film coating on it so that there's no reflection, and they are really efficient. All of the light then, especially if you're doing it in a narrow range of wavelengths, all of that light goes into forming your image or goes into that application. You don't have orders. But when I deal with diffractive optics, I could have many orders and I'm using only one order. So there's always it's always less efficient. I could have multi-level diffractive. I can improve the efficiency of the diffractive optics. But in general, I would say refractive optics is really very efficient. So I'm not sure if that answers your question. Please feel free to ask or type in the chat again if that doesn't answer your question. The advantage I was trying to say in the last part of my talk is that meta-optics has some advantages because I can create multi-level of phase and come close to the refractive. A refractive element, let me see if I can get back to. So if I take a refractive element like this, the phase variation is smoothly varying. It's continuous and smoothly varying. That's really what I want with the meta and the diffractive. But I can't make so many levels. So I just make 2 levels for a binary diffractive. I could make many levels, but it increases my complexity. It increases the difficulty in fabrication. But in meta, just 2 levels, but different sizes gives me all the phase levels. So I can be more efficient with easier fabrication in meta optics than in diffractive. But overall, refractive is often easier, more efficient. Can you elaborate on multi-layer mirrors? So multi-layer mirrors is quite a different concept. So you have thin layers on the mirror where you're using interference between those layers. Those are not diffractive, these are not meta optics. You're actually using interference. So you have many layers and you have interference from each of those interfaces, and you can design the thickness of those layers such that the different beams coming from each interface coherently or constructively interfere. So the technique, the idea is very different. It's not a diffractive element at all. You're using the ideas of interference, not diffraction there. So does that answer your question? So it's also a completely different technology. At least in our department, we don't have the ability to make that coating. And the design, you need a totally different design skill. I think some people in the physics department do work on that, but that's not a skill those are not facilities we have in our department. And can these principles be used in radio wavelengths? Yes, in fact, many of these principles are used in radio wavelengths. The first meta optics were used with much larger, lot of meta structures. One of my students worked with someone in Australia and he did work in terahertz. So the structures themselves, the elements are in tens of centimeters and it's very easy to fabricate. The feature sizes there are large. So yes, they can definitely be used with the larger wavelengths, and they can and they are used. So someone has asked, can the work be used to shape light over a range of wavelengths? This is a problem because diffractive optics, meta optics, because they're so, the way the phase change is done, they're very sensitive to the phase, and the phase is a function of the distance traveled. It is of course a function of the refractive index and the wavelength. And for diffractive optics and meta optics, a change in wavelength means the phase change is very large. So to make a single element that works for a large wavelength range is not, it will not easily work. Having said that, there are some techniques you can use to help design elements that work for a certain set of wavelengths. So you can take a diffractive element that works for some multiples of wavelengths. They're called harmonic diffractive elements. You can take make a diffractive element that in the first order works at one wavelength, in another order works at another wavelength. You can design a meta-optical element. I showed you meta-optical elements with simple cylinders as the small structures, but you can have meta elements where the structures are not just cylinders. Maybe they are crosses, or maybe they are a V-shaped structure. And you can have two cylinders with a gap between them. So you can have a very complicated meta-atom. These little structures that form part of a meta surface are called meta-atoms. You can have a very complicated meta-atom, which will then have one phase for one wavelength and be able to provide a different phase or the same phase for another wavelength. So with the complexity becomes much more. You can definitely, people have done it for two wavelengths in meta-optics. Efficiency may not be the same for both wavelengths. So a simple answer to that question is you can, yes, for a limited number of wavelengths, but that's quite a hot topic of research right now. People want to make meta-optics that work over a very broad range of wavelengths, and there is work going on in that right now. Whether this technology can be used in the flex road technologies. I'm actually not sure what the flex road technologies are. So I don't think I'll be able to answer that question. If there are any other questions, I can answer them. I think I've covered all the questions.
Do we have any other questions? I think somebody has said something. Okay, thank you. Right, okay. Thank you so much, Professor Shanti. This is such an informative session. I think you were able to hold interest so well, and I think we had a number of questions. Thank you so much for your patience to answer all our questions, and looking forward to collaborate with you in future again.
Thank you. Thanks a lot for arranging this.
Thank you so much. Thank you. Yes. Thank you, everybody who joined the session. Many thanks. Have a great day, great evening, and a great weekend, everybody.